Hello. Hello and welcome to this session of Spring into STEM. My name is Vanessa Diaz and I am a professor of healthcare engineering and also the Vice Dean for EDI, Equality, Diversity and Inclusion in the Faculty of Engineering Sciences at UCL. So I'm going to be talking to you this morning and hopefully we'll have a nice chat about what engineers do in healthcare and how we help clinicians do their job. So the title of my talk is "The Engineer Will See You Now," and we are actually designing the future of vascular surgery. So what does the future of medicine look like? And is this science fiction really, what the future that we envisage? And we, at least for people in my field, we envisage people, you and I, living inside a computer, and it's not us not having a presence in the physical world, but having a digital twin that lives in computers in hospitals where we store data, medical data, we keep track of our medical records, and also we perform virtual interventions to these patients before the actual interventions have to happen to these patients even. So right now, the situation is quite different. So in June 2022, so we are in June, this is what happens. Let's say that a person arrives at hospital with chest pain, pain in the legs, etc. So lots of people ask you lots of questions, many times. And then there are some scans that show, for example, a dissected aorta. And I will tell you what a dissected aorta looks like and what it is in a second. And then the doctors decide the treatment, then that might be a surgical intervention or not. And then they send you home, and that's pretty much it. So it's very substandard, I have to say. So we address the immediate problem or the acute episode for a person typically, and then we just let patients go. But we imagine a pretty different future where things are going to be much more like Star Wars, and we're not there yet, but we're making headway into that future. So let me tell you what an aortic dissection is like, because that's the example I'm going to show you today. It's not the only thing that we work on, but we do work on aortic dissections a lot. So an aortic dissection is a rupture in the tunica intima of your aorta. So imagine that you have a tire, and then you have many layers of that tire, and the tunica intima is one of the layers, and there is like a puncture in that layer. But instead of deflating, that fills up with blood, and you end up with blood in the tunica intima, and that actually expands, and you create a big aneurysmal region. So it starts flowing, so the blood goes inside and starts growing and growing, and then it can rupture anytime. So this new region that is filled up with blood now is called the false lumen, and the true lumen is where the original vessel would be like. So the prime target is the aorta because it's the blood vessel where the pressures are highest. And the causes are, for example, chronic hypertension due to stress, high blood volume, so for example, pregnant women, or coarctation, so you have a natural narrowing of your aorta. That will also mean that a dissection might be likely. So if you have a dissection in the first part of your aorta, in the first 10 centimeters or so, so in the upper part on the ascending aorta, that means it's a type A, and otherwise if you have it anywhere else, it's a type B dissection. And actually you can have a dissection anywhere. And the dissection can expand, so it's not like it just creates a little sac and it stays there. So the tear continues and it can dissect many other blood vessels, for example, the renal arteries and the arteries that we have in the legs. So, and it's quite deadly. So it has to be treated immediately, and the treatments are very personalized. There are no two dissections that look alike. When medical students, they go into medical school, they rarely see a dissection, and no two dissections are the same. So they are very individual events. And I'll show you some awful cases of dissections. You can have many what we call fenestrations, so many punctures in that aorta in many different places. So it creates a real challenge for the clinicians to know which way to treat, what is the best way to treat these patients, how can we get them up and running again. Many of these patients, by the way, will end up dying because either the dissection will be misdiagnosed, so people don't recognize it when so the clinical teams, they might not realize that it's a dissection. The symptoms are quite generic. It's similar to a heart attack, but not quite. So unless people have the scans, the clinicians won't know. So how can engineers help? So this is the typical pathway of a chronic type B. So remember the dissections that go on the descending part of the aorta. So after an acute episode, so that means after the dissection happens, if people are lucky enough so that the clinical team or in A&E, they realize that this can be a dissection in their image, then the next thing is that they will observe what happens with the patient. They will try to stabilize blood pressure for sure. Blood pressure is a huge thing in aortic dissections. They have to absolutely control the blood pressure, because the more blood pressure you have, the more pressure you have, the more the tear can expand, and the more of the rupture will enlarge. So they will control the blood pressure, and then they will typically have a follow-up clinic where they will see whether they can get the dissection stable or not. So, and then they will discuss options with the patient, and there might be some treatment involved. So that means that if for many patients, this will involve actually a surgery, is a heavy surgery. They will have to cut parts of the vessel and replace them with synthetic materials like Dacron, for example. They can also tailor some of these to the patients, and they can replace parts of the aorta, but they tend to not replace it all, because the aorta is a critical vessel that supplies a lot of blood to the rest of the body, and oxygen, of course. So if you replace a natural material that has many tiny connections and large connections as well with key organs, but also lots of tissue, you might end up being with what we call malperfusion. And that means that you don't get enough blood where you need it. And that creates all sorts of problems. So after you discuss the options with the patient, then they intervene. So it can be, for example, open repair or endovascular. So that means that they will open the patient up, or they will go with a catheter and try to patch up this aorta without creating a, opening the patient completely. And then there will be final scans and follow-up. So we imagine a future that is a bit different from what happens now. So a person arrives to the hospital, then there is a digital twin, and the digital twin is continuously updated with your medical data, etc. The scans will show a dissected aorta, that those scans will now be stored somewhere and they will be kept on record. So we'll do multiple testing of the virtual outcome of the virtual outcome of the virtual U. So we'll test many different operations. They will test many different things that they can do to you. Then with the patient, we'll decide what is the best treatment for the right patient at the right time. And then the patient is discharged, but monitored remotely, and the information is constantly updated. So I know that this sounds like very far in the future, but actually we're making quite a few steps forward in along this vision. So we have an approach in practice, and I'm going to tell you more about it in a second, where patients will have an intervention, let's say, or so we know the patient comes and the outcome is that they might want to have an intervention. So we have in vivo data, so data, clinical data, so scans, CT scans or MRs. Then we have a simulation model of the patient where we'll simulate a virtual intervention. So we do surgical scenario testing. Then we'll 3D print your aorta using different sorts of materials. And we'll test your intervention in a realistic physical environment. And then we'll provide and quantify and examine the different interventions that the clinicians might want to see, and we'll present the options to them, and then they will discuss them with you. And then they will decide with you what seems like the best possible options for them then to intervene, right? Or maybe the decision is not to do anything at all. So this is us in the hospital. So we work very closely with clinicians at the Royal Free and also the Barts. And you can spot the engineers because we don't have any. We don't have any medical gear on us. And this is us with, so this is me with my colleague, Stavrula Balabani, and then with one of our students. So I'm part of the mechanical engineering department. And I'm also part of the WISE Center, and which is a center dedicated to interventional sciences, so engineers working with clinicians to provide solutions, engineering solutions to medical problems. And we, for example, had an event called the Science of Surgery. You can contact us in WISE if you're interested in this type of activities, and you can come with your children or by yourselves, and we always are very happy to explain what kind of work we do. So now back to the cases. Let me show you what an aorta, a dissected aorta really looks like. So we have the CT data, so we have all the scans with everything in between. So you have the heart, you have the pelvis, everything. So we extract the geometry. So we extract the aorta, which is the part that is of interest to us. And in this case, you will see that there is a dissection that has an entry tear. So that means the puncture was done in this place. And it will continue down to here, where it will form a kind of an aneurysmal, so a big balloon, that in this case, it doesn't really go anywhere. It's just, it stops there. So it had an entry there and nothing else. And then you have the true lumen and then the false lumen, as we discussed before. So we get the clinical data, so scans, some MR data in this case. So that means that we have seen MR, so we can see how the aorta expands in real time. And we also have some flow to PCMR. So in this case, we could see also what the flows were in the aorta, and some pressure measurements. Now, there are other cases in which the aortas are very complicated. The dissections are complicated cases. For example, let me show you 3 patients that we got from some collaborators in Rome. And in this case, you can see that these are very complicated dissections. Let's look at patient 3, for example, where you have what we call 21 fenestrations that we could see. So that means 21 punctures, large and small, along the aorta into the vessels that feed your legs, which are these 2 at the bottom here, for example, and in the renal arteries, around the renal arteries. So, I mean, you can see how completely different and actually diseased this vessel looks like compared to a real aorta that looks pretty much like a lollipop. It has a lollipop shape with some arteries feeding from it to deliver blood to organs like the kidneys or the liver, for example, and definitely the neck, which are the arteries that you see here at the top. So we simulated this aorta, the first one that I showed you. So that was the first case, one of the first cases that we simulated. And I'm showing you here what CT scan looks like. And we had very, very good results in predicting what the pressures were in the true lumen and the false lumen. By the way, it is important for the clinicians to know what the pressures are in this disease part, if you like, in the part that looks more like a balloon, because they cannot really go with a catheter in and measure it, right? And because the higher the pressure, the higher the risk is that this will rupture, and that will be catastrophic if it ruptures, right? They don't go with a catheter to measure the pressure, but we can do the calculations for them, for example. And then here, we, in our models, although you do not see it here, we basically try to reproduce the, and we capture well, actually, the movement of the aorta, which is an important thing, and I will tell you why, at least in this case. So we had what we call a rigid wall model. So essentially your aorta doesn't move. It's like a tube of, it can be even a tube of metal, right? And we can do some fluid analysis on that. But if we have the compliant models, and that means the models that expand with pressure and flow, that means that we will be able to see some subtleties here that are important. So you can see that in the compliant model, we predicted we predicted different pressures in the true lumen and the false lumen, right? So we predicted a higher pressure in the true lumen and smaller in the false lumen, but there is a swap at some point. So they cross, right? So that means that the pressure in the false lumen is higher after 0.34 seconds. So you can see here when the division between the two of them, so you can see one is compressed and the other one expands. Whilst in the rigid wall model, you couldn't really see that. And the important thing for this patient, for example, this was a 70-year-old patient that had a dissection for many years and he had never really thrombosed. So that means that the dissection always had blood going into it, maybe a little bit of thrombose, so blood clots, but it had never really completely resolved. And it's because we could predict with the compliant model that there was flow going in and out, and it's because of this expansion of the vessel that was allowance of movement of the blood that otherwise would not be possible if you only had rigid tubes. So I can also show you lots of beautiful pictures about flow. For example, all the swirling that we have in the true lumen and the false lumen, for example, which explains why maybe there is no thrombosis or that there is no significant clots that kind of resolve the dissection by itself. I mean, that's the best medical outcome. The natural resolution of the dissection is that the vessel, the blood, there will be thrombosis. So that means it will be completely blocked naturally and they won't have to do anything to it. And then we calculate things that are of interest to clinicians, and these are what we call hemodynamic biomarkers. So, but now, remember the slide that I showed you before, we have the same patients, both in vitro. So we can actually take this shape of the aorta, 3D printed with materials that some are rigid, like the one that I'm showing you now, but also we're working on expansible materials that are transparent. So we can do some analysis on them. And we put them in a flow circuit where we reproduce or replicate the conditions in the body. So basically, we try to get as close to as the real situation for the patient in the lab. And we're going to seed the flow. So we're going to put flow through these 3D printed aorta and seed it with particles. And we're going to have fluorescent particles that then we are going to image by putting a high intensity laser through it. So we're going to be able to know where those particles are. And from there, we would be able to calculate velocities, pressures, etc. So this is what the setup looks like. This is a pump that emulates the heart. These are two real mechanical heart valves. So we have the, this would be the mitral and the aortic valve that then connects to the 3D printed aorta of that specific patient that you see there. And all these connectors and tubes, what you see there, they represent the rest of the vasculature because we have compliance everywhere and we have resistances and inertia everywhere else. So, and then we can study this in the lab. So I'm going to show you some of the experiments and simulations and the comparisons between the two. So this is, I'm showing you the most interesting ones, which are what we call at the end of diastole. So you have a peak, so your heart pumps, and then you have a peak, an increase in pressure and flow, and then you have a drop. And this is after the peak. So I'm showing you what we call mid diastole and end diastole. And this is what the blood flow looks at mid diastole. And then you can see, we can see that the comparison between the experiments and the simulations are very good. So we have a way to validate or to say how good our predictions are using computers of the decision or the surgical decisions that the clinicians have chosen for the patient, right? And then I'm showing you at the end of diastole how disorganized the flow is with many, many different currents going inside of the vessel at every time and everywhere. So this is the comparison at 4 different planes. And we also compare what the velocities were, and they, this essentially tells us, without going too much into detail, that our experiments and our simulations, they go hand in hand and they are very good. And what we can simulate in the computer, we can replicate in the lab. And this gives a lot of possibilities for the clinicians to explore manually on the setup that we have, and also to inspire them with confidence that the solution that we're getting is something that is sound and they can trust it. So to conclude, I'm going to conclude here because we can go on and on about the results that we have, but we are changing medicine for the better. The clinicians rely on a huge amount of training and skill, but understanding the human body is an incredibly complicated task. And we as mechanical engineers use a lot of skills to design better systems and to understand disease and health. But honestly, the best part of my job, and we do this very often, we collaborate with patients and with patient groups, and I feel really inspired to keep going. And this is all very hard and it's hard work, but they give me the motivation to continue and to try to do a little bit better every day. And being able to help, honestly, is the best feeling in the world. So I'm going to stop now, and I'm gonna stop sharing my screen, and then I'm very happy to take any of your questions. Thank you. What is the computational cost of these simulations and the corresponding running time? So, so the simulations, they take obviously longer in the compliant case, so they can take a few days compared to maybe, so let's say up to 5 days, let's say. I mean, it's very case dependent and how big your mesh is, right? So I'm assuming that you come from, so I'm going to assume that you are so the person who's asking me this question maybe knows a little bit of how these models work. So basically you take the geometry and you break it down into very, very small elements, and you need to simulate millions of elements simultaneously. And that's why the more complicated your case, the more finesse you need into breaking what we call a mesh. So you need smaller elements to capture really the finesse of those simulations. And they can take up to a few days to run on the cases that we have, compared to maybe a couple of days on the rigid case. And the cost of the simulations, so we can run them in PCs. So if we have many simulations to run, we send them to a cluster, but we can run them in our own desktops. Now, something that I didn't mention because I didn't have the time is that obviously, so these timescales that we have, they actually work with the type B dissections that we have, because the timescales are long. By the time the patient comes to when they have an intervention on, it will be about 6 weeks. So these timescales work, but we're trying to get our simulations to run much faster. And I am working with my colleague Stavroula Balabani that you saw there to use some data-driven methods to look at complicated cases like dissections that should be real-time or near real-time. So what inspired you to pursue your area of research? So I guess I was good at solving problems, and I thought that engineering might be a good career for me. Then I went into engineering, and I really did enjoy the more theoretical aspects, but I realized that cars and turbines, they were not necessarily for me. But there is this other world for mechanical engineers that is bioengineering, and I was always, I felt I need a strong sense of purpose to do my research. So something that gets me out of bed and say, I'm going to do some good in the world. So, and that's, so in a way, so it's a mix of, so there is some serendipity, right? So you meet people, you talk about things, and then you say, I really like this, and you pursue some things. And then I decided I wanted to do a PhD in bioengineering. And then I ended up meeting clinicians who were then interested in dissections, and I'm working on dissections. It's not the only thing that we do, but that's how things work. Now, at the start, it was just, I was an engineer that was eager to do some good in the world. And for me, the choice was between being a doctor, a medical doctor, a proper doctor, and an engineer. And I went for engineering, but then I came back to the things that I really love. So yeah. Oh, what does a typical day look like for you? There is no typical day. So I have to say, research is a lot of frustration. So you go in every day and you keep going and going. Things, they tend not to work 99% of the time, but then, oh my God, you absolutely leave for the 1% when things actually go well, because it is a lot of hard work that gets you to a result where you say, or to develop a method that you actually say, I trust this and this is good, and look at the results that I'm getting, wow. So it's very rare that you experience like, something sudden, like I'm gonna do this, like in 2 hours, it's gonna be amazing. I mean, I've never seen anything like that, but my day-to-day is very, so there are no 2 days that are the same, but they all involve a huge amount of resilience and to keep going at problems, I would say.
Thank you everyone for joining us today. And if you want to find out more about our future Spring into STEM talks, we have an events webpage on UCL Mechanical Engineering. Just give us a search. You'll find some other talks there. So yeah, please do check back. And from all of us here at UCL Mechanical Engineering, thank you for coming, and hope to see you again soon.
Thank you very much. Thank you very much for having me. Bye.